Hello everybody, good afternoon. My name is Matteo Castellani. I'm from the Department of Civil and Environmental Engineering of the University of Perugia. It's a pleasure for me to present this work titled Dynamic Identification of the Tabernacle of the Church of Santa Maria Maggiore in Spello, Italy. This is the outline of this talk. First, I give you a brief introduction and motivation for this work, then some details about geometrical survey obtained with the integration of laser scanning and UAV photogrammetry. Then I will show the dynamic identification process of the tabernacle obtained by dynamic identification in ambient vibration and free oscillation test. Finally, I will conclude this presentation with concluding remarks. This work was born as a part of the restoration and consolidation intervention of the Church of Santa Maria Maggiore in Spello and, in particular, of the High Altar Ciborium. The Superintendents of Archaeology, Fine Arts and Landscape of Umbria has entrusted the Department of Civil and Environmental Engineering of the University of Perugia Laboratory of Structural Dynamics with the task of execution of experimental investigation on site for the dynamic characterization of the ciborium of Santa Maria Maggiore in Spello and related numerical elaboration, aimed at identifying the frequencies relating to the first mode of vibrating and the corresponding modal forms. The conservation of architectural heritage is a primary concern for the preservation of the cultural identity of a population and one of the tangible proof of historical architectural development. In most of the cases, architectural artifacts must be protected over time from all the threats that could derive by both the variation of inherent properties, as the aging of the constituent materials, and external action, such as natural hazard and strong events, typically earthquakes. The preservation of architectural heritage against seismic events requires an in-depth knowledge of its dynamic properties, which can be affected also by local damages and material degradation. The tabernacle, made of caciolfa stone, has been built at the beginning of the 16th century, and it is characterized by 4 columns of about 3 meters high that supporting a 4-stone arch on which a hemispheric dome rises, reaching a total height of about 8 meters. In plan, the structure has a square regular shape with each side of about 4 meters length. The architectural artifact has been built by connecting stone elements through internal iron bars, resulting in a multi-block structure with a complex dynamic behavior. The main purpose was to verify any non-linearity effects and to analyze the motion in free oscillation of a multiple object, such as the ciborium. An important material identification campaign was conducted in 1994 through non-destructive tests after the earthquakes that hit Umbria. Thanks to those tests, it was possible to ascertain the degradation of the material located at the base of the columns and in the walls of the plan, in which its basicity was lost due to the carbonation process. This, over time, has led to the degradation of the internal metal skeleton, a closed square frame that follows the plan of the arch and its consequent oxidation due to the material degradation of the plume walls. The decay also affected the common shutter of the west and south arch, resting on the southwest column, with cracks in north-south direction in the area between the 2 tie rods. This led to a 54 reduction of a propagation speed, which represents total damage of the stone structure. The support plates of the 4 columns of the ciborium have visible cracks on the internal side of the plate due to the movement of the ciborium during seismic events that stress the plates in pressure bending with the eccentricity of the load outside the central core, thus inducing tensile stress. It was possible to observe a state of widespread decay, also located in the joints at the base of the pillars, which can alter the dynamic behavior of the structure. An important role for the historical conservation of the cultural heritage is entrusted to the three-dimensional reconstruction of the build through the innovative technique of laser scanner combined with UAV photogrammetry in extremely confined settings. With an acquisition time equal to 6 minutes and 50 seconds, a dense cloud of points of the substructure was created, on which the dense cloud obtained with the AEV photogrammetry made using 71 photos taken in manual flight was superimposed. The synergy between these two different methods allows to assess with high degree of confidence the geometry of the build, essential in the reconstruction process of a digital model, the foundation of the successive analysis. The dynamic identification campaign was conducted over 2 different days with the aim of characterizing the dynamic behavior of the tabernacle and verifying the presence of any nonlinearity phenomena.
High-sensitivity piezoelectric accelerometers were used mounted on steel angles to allow biaxial measurement configuration for a total of 24 channels divided into 3 different setups. The 3 setups consist of 10 acceleration sensors each, 3 of which have the function of reference transducer channel 1, channel 2, and 3, that is kept in a fixed position in the various setups. In this way, it was possible to carry out a dynamic identification of the 24-channel structure. The 3 instrumented levels are the base below the grafting section of the columns, the tax base of the arch, or the section above the capitals of the columns, and the top floor at the base of the dome. The MOVA software implemented by the research group of the Department of Civil and Environmental Engineering of the University of Perugia was used for dynamic identification. The signals were pre-processed using a Butterworth bandpass filter with a frequency interval of 0.250 Hz of second order and resampling at a frequency of 100 Hz. The dynamic identification was performed in the time domain by means of the technique of stochastic subspace identification. In addition to the first 3 structural global modes consisting of the first-order bending modes and torsional direction, 2 other modes at higher frequencies of type have clearly been identified global due to the multi-connected nature of the artifact. In particular, the M1 mode involves the stone blocks of the upper part of the ciborium consisting of arch, the overlying structure, and the dome, while the M2 mode is located on the supporting pillars of the structure. The results highlight the multi-connected nature of the artifact, even in the regime of small displacement and deformation. In fact, by focusing attention on the pillars, all the model shapes have a broken line at the joints of the columns, which is more evident in the high-frequency modes. In addition to this, a quasi-static firing test was carried out in which the ciborium was subjected to an increasing force applied to the height of the shutter of the arch, or at the top of the columns, by means of a rope. The purpose of the test was to verify any nonlinearity effects and analyze the motion in free oscillation in terms of oscillation frequencies and amplitude of displacements. The instrumentation used consists of a strain gauge load cell used for measuring the pull in the rope and a displacement transducer for measuring displacement in specific point considered of a particular interest, as indicated in the diagram below. In particular, the pull was applied at a distance of about 6 meters and a height from the ground of about 1.50 meters, so that the effective part of the applied force was calculated as the horizontal component of a vector inclined of about 15 degrees on the horizontal. The displacement transducer have been positioned both at the top of the columns, that is, near the point of application of the load, and at the base of the 4 columns, in correspondence with the joints with their respective bases, possible site of rocking motion due to the formation of localized hinge.
The graphs below show the force displacement equilibrium diagrams obtained from 2 different shooting tests. In particular, the horizontal displacement data obtained from the sensor 1 and sensor 2 are compared with the vertical data relating to the sensor placed at the base of the columns, sensor 5 and 8, indicative of the opening-closing of the hinge. The graphs show how the two measures of horizontal displacement are consistent with each other, taking into account the levels of uncertainty present both in the symmetry of the stiffness of the structure and in the direction of the applied pull. Similarly, the opening and closing measurement of the hinge can also be considered consistent except for the measurement point relating to the sensor 6, which locally has a lower level of degradation than the others.
A rigid motion kinematics is therefore hypothesized as illustrated in the present figure, in which the displacements are condensed exclusively in the base and top joint of the columns, and the rotation is activated around a hinge placed in the center of the section. It can be deduced that the dynamic of the product is characterized by the presence of further localization of deformation, in addition to the one found at the deformation of the constituent material. The application of the pull at the top of the columns made it possible to carry out an analysis of the motion of the seaborne in free oscillation, starting from an imposed displacement of about 1 mm. The graphs show the time histories of the displacement measured, which show an evident oscillatory motion of the columns on the base pin. The frequency spectrum of the time histories shown in the figures on the right shows a period of oscillation clearly evident in all signals with a frequency around 1.84 Hz. Comparing this value with the first frequency identified in ambient vibration, which corresponds to a flexural mode formed in oscillation consistent with the motion imposed in free oscillation, a decrease of more than 20% is noted. On the basis of the measurement performed, it can be deduced that this difference is linked to the presence of a rocking motion between the constituent elements of the monumental seaborne, which, moreover, is manifest by very limited displacement compared to what could be observed under horizontal action of high intensity.
Finally, let's finish this presentation with some concluding remarks. Three modes of vibrating have been clearly identified, the first two of the flexural type, along the direction parallel and orthogonal to the ace, respectively, and the third torsional. The model forms manifest a disjoint motion of the blocks that make up the structure. The free oscillation test highlighted the presence of a localized rotation motion of the columns around the connection joint. This motion is characterized by an oscillation frequency lower than that identified by identification test in ambient vibration of over 20%. The structure under investigation is characterized by non-linear dynamic properties, the characteristics of which are manifested even in the presence of small displacement. The results, also strengthened by the outcomes derived by different non-destructive tests carried out about 20 years ago on the constituent materials, which emphasized the degradation state of the stone material corresponding to the most stressed areas of the joints, have highlighted the crucial role of diagnosis with a multidisciplinary approach in order to achieve proper decision of intervention in the respect of the cultural heritage. Thank you for your attention.